Okay, so thank you very much, and hello everybody, I'm Edoardo, he's Daniel, and today we are going to talk about Mediatek Wi-Fi hardware and how it's possible to unlock hidden superpowers by exploring its firmware. And a small disclaimer before starting this talk, our opinions are our own. So, well, let's start to introduce our motivation and goals, because we are going to explore a new hardware with almost no previous research on it. And well, we want to enable new mood and feature, we want to play with the hardware, we want to understand how does it works, and well, our main goal for this talk and also for future talks is to improve the future of the Wi-Fi physical layer research. So, well, let's talk about Mediatek and the previous research on it, because essentially most of it had been done for smartphones. For example, in 2021 there was a secure boot bypass exploit which was found in Mediatek boot ROM for Android smartphones. And well, then the baseband of Mediatek had been explored several times, and the baseband essentially is the hardware which managed the 4G and 5G communication. And also the kernel ecosystem of Mediatek hardware had been explored, and well, for example, an exploit was found in its audio DSP kernel driver, but well, until now nothing had been done for the Wi-Fi firmware. So, well, we are the first essentially. And if we want to talk about Wi-Fi firmware research in general, we have some history, because for example in 2019 the Nexmon team worked on Broadcom hardware and they were able to enable CSI mode, which is cool. Then in 2022 was the turn for Intel hardware and it was exploited. And Daniel in 2023 worked on Qualcomm extensor based routers, and he was able to use Nexmon on it. And well, in the last 2 years a lot of effort had been put for implementing layer 2, which an open source layer 2 in the ESP32 Wi-Fi firmware. And well, this is quite cool, but well, now we need to ask ourselves, where can we find Mediatek hardware? And well, the answer is almost everywhere. We can find it in smartphones, smartwatches, non-Intel laptops, and USB Wi-Fi dongles. For example, there is one which is quite famous and is Wi-Fi 6. And also OpenWRT routers make use of Mediatek chipset, and well, it's possible to use a single PCI cards for, as a Wi-Fi hardware and attach to the computer, and well, it will work as a Mediatek dongle. And well, now let's start to talk about Wi-Fi chips in general and how does they work, because usually they contain their own real-time operating system, and there is a communication between the host device, which essentially is well, our operating system, which can be Linux, Android or Windows, and the Wi-Fi chipset, which is in this case an Andes MCU. And essentially everything starts from the user space where you have an application, for example a browser, and this browser requests some data, and well, it sends a request to the kernel, it will open a socket and so on, and then the kernel will start to process the request, and essentially the driver, which is a piece of code which knows how to communicate with the hardware, will interact with it, and well, it will talk to the firmware, which is composed by a ROM and a RAM essentially. And well, if we want to talk about drivers for Linux and Android, we have two main distinct drivers. So the first one is called MT76, and is the mainline driver for Linux. It supports almost every devices ranging from Wi-Fi 4 until Wi-Fi 7, which is the latest one. And its code is very clean and minimal, and well, it offers a debugging interface under CFS, so you can interact with the driver. You can also communicate with it over netlink, so user space to kernel space driver communication, and it's possible also to enable some patches, but those are for OpenWRT, and as a result you get a better experience with debugging essentially. And on the other side we have Gen4M and MT Wi-Fi, and those two drivers are quite similar, and they are used for IoT and Android. So well, They are used mainly in the embedded systems, and well, they support almost every device ranging from Wi-Fi 5 until Wi-Fi 7, and its code compared to MT76 is well, more verbose. It has a lot of comment, a lot of features are not enabled by default, so you need to play a little bit with the kernel driver. And well, it offers a better communication interface because you need to use IOCTL, which is deprecated in my Linux operating system, but well, you can interact with the driver in Android by using a tool called iwpriv. And well, let's talk about the firmware now, because we want to understand why we need to look at it, and essentially because we want to find answers. Essentially everything which isn't defined at the driver level usually is defined at the firmware level. And well, we want to understand which interfaces are supported by the firmware, and does it exist a special development or factory firmware which has more feature compared to the default one. And well, if we want to talk about Mediatek Wi-Fi firmware, we have at least three distinct times. For example, initially for Wi-Fi 4, the firmware was an ARM32. Then it moved with an Andes NDS32, and this was like from Wi-Fi 4 until Wi-Fi 6E. So essentially every chips in this talk will use this instruction set architecture. And well, then the really latest chip make use of a pure RISC-V architecture, which is an Andes N45, still the same system on chip but different ISA. And well, let's talk about this ISA. So it is a big endian, the RISC-V inspired. Is a load store based instruction set, and it permits to mix 16 and 32-bit operations, and well, it permits to extend it. It has some custom extension, for example the DSP and the floating point unit extension, and it has 32-bit general purpose registers, and the three most important are the number 29, which is the global pointer, and essentially it holds a base address for indicating that there is some global data after. So when the firmware needs to access some global variable which are very used, essentially it reads the base address from this register. And then there are other two registers which are quite common between assembly language, and those are the link pointer and the stack pointer. But if you want to understand more this ISA, essentially you have some online resources, because for example there is the official ISA manual from the Andestech website. Then you can, for example, find on their GitHub the ZCC and binutils, which are quite cool because you can both compile your C code and then get a disassembly of it, so it can be quite useful. And then we have also a Ghidra processor module which permits to get a decompilation of the firmware, and this is even good because you can grasp it even better. And well, if we want to talk about the firmware we will be dealing with during this talk, we have essentially four firmwares blob. And well, the first one is called the ROM patch, and this firmware is like a pre-initialization code for the RAM, and is loaded at an early stage of it, and well, essentially is placed after the ROM code, and it contains additional callbacks, and essentially it permits to handle some features, for example the core dump or other pre-initialization code for preparing the RAM firmware loading. Then we have two firmwares which aren't commonly used, and those are the wireless offloader and the wireless accelerator. And well, essentially they are on their own CPU core, and for using them you need to enable some specific MT76 patches, otherwise those firmwares won't be loaded normally. And well, their main purpose is to enable the WED, which stands for Wireless Ethernet Dispatch, and it permits to enhance the throughput and decrease the latency. And the WO firmware is mainly used for the processing of wireless frames, so the receive path, while on the other side the WA firmware, also called wireless accelerator, is used for the transmit path. and well, is used for the layer 2 mainly of the WEID. So essentially it handles only the transmit of the data over, you know, the area. And then we have the WM firmware, which is also called wireless main, and well, most of the hardware make use only of this firmware and of the ROM patch. And well, essentially this can be used as a standalone firmware, and it contains almost everything for the proper working of the Wi-Fi hardware. So it has the FreeRTOS code, which is the real-time operating system Mediatek choose to use for its hardware. And then it contains the command handling interface and everything related to the receive and transmit path of layer 1, 2 and 3, essentially. And if we want to talk about its format, essentially it has a trailer at the end, and the trailer is like an header. It contains the metadata of the regions, and a regions essentially is a piece of code which is sent to the ROM for initializing the RAM firmware. And essentially you can find some metadata, so the data length, the flags of the regions, and essentially the offset of the starting point of the region. And well, now let's talk about the firmware loading, because essentially when you attach your, for example, USB dongle to your computer, there is a pre-initialization phase where the driver talks to the ROM. And essentially the driver sends a semaphore lock request to the ROM, and then it starts to send the ROM patch, which is used for the pre-initialization phase of the Wi-Fi firmware. And then when this phase is finished, essentially it closes the semaphore, and well, it starts to send the RAM firmware. So it will start to parse it, and for every region it finds, essentially it will send to the ROM. So it will send the length of the regions data, and some regions flags, because for example you need to indicate that a region is the starting point of the RAM firmware, or for example there is some code encryption, so you can indicate that this region is encrypted and the ROM will decrypt it at runtime. And well, when this phase will finish, essentially the ROM will jump to the start of the RAM firmware, and your Wi-Fi hardware will start to working normal, I think. And well, let's start to talk about also the communication between the kernel and the Wi-Fi RAM firmware. In this case, our host is Linux, but it works for also Windows and Android. And for example, let's put that you need to access the monitor mode or the access point mode. Essentially, the host will send a specific packet to the Wi-Fi RAM firmware, and the most important field of this packet is represented by the so-called SID or command ID, which essentially is a 4-byte integer. And this is the code which essentially permits to recognize the feature you are requesting. And well, essentially the Wi-Fi RAM firmware has an hardcode table which is called command table probably, and essentially it will do a lookup for every command ID. It will find a function pointer, and it will call it, and this function pointer will execute the operation you are requesting, essentially. And then it will send the result to the host again, but this isn't important. And now, well, let's talk about firmware debugging, because we want also to understand how does the firmware works, and well, how is possible to communicate better with it. So we have some tricks we have found. For example, we can get the firmware logs, and this works by sending a value between 1 and 3 to a specific file in MT76, and this under the hood will send a specific command called the firmware log to host to the Wi-Fi MCU, and as a result you will see the kernel log, Wi-Fi firmware logs in the DMESG at runtime while the chip is running, and this is extremely interesting because you can understand what is doing your Wi-Fi hardware at a specific moment. Then you can also request a crash dump, which essentially sends an assert command to the Wi-Fi MCU, And well, as a result, you will get a crash dump to the kernel, and the drivers know how to save it. And after this operation, the Wi-Fi firmware will start again. And if we want to examine this core dump file, essentially is a 1 megabyte binary file which is split in two parts. The first one is the text part, and is let's say the most important. Then there is just some binary data. And the text part contains the backtrace of the last 32 function executed before halting the firmware. And in those strings you can understand the function flow. This is cool. And also you can get also the register state of the RAM firmware, and this is good too because you can get the global pointer address, which is extremely helpful when you need to reverse engineer the RAM firmware. And then, we have the reg index and the regval trick. This is quite important because essentially it permits to write and read a specific portion of memory of the Wi-Fi chipset from the user space. And essentially it works by writing a value to the reg index file, and this will set an address you want to play with, and then you can manipulate it with the regval file. So you can, for example, choose to read it, and you will read the memory of a specific offset in the Wi-Fi RAM. Otherwise, you can also try to overwrite it, and this, it permits to customize the firmware while it's running. And the only caveat associated with it is that you can always play only with 4 bytes at once, so you need to iterate certain operation. For example, if you want to dump the ROM, you need to iterate this process for some time before getting the full ROM. And then we have found another interesting trick, but this wasn't present in the Linux driver. It was present only in the Android driver, and it permits to read the program counter state while the RAM firmware is running. So you don't need to ask for a core dump for getting the register state. You can just get those registers at runtime, and this is quite interesting too. And now Daniel will start to talk about HiCap and CSI mode and how it's possible to unlock them on Mediatek chipset.
Thanks, Edoardo. So before we can talk about the actual unlocking, let's get some basics of Wi-Fi out of the way. So how do we even modulate data or encode data within Wi-Fi? So the first example I have here, or which is important later on, is phase modulation. So you can see here, I just basically sent 2 sinus waves twice for a 0 in this case. And then if I want to send a 1, what I do is I just basically start sending the sinus wave at a different point in time. This might be a bit confusing, but this is all there is to phase modulation. So you're basically just moving where you start sending the actual data. But this can already be used to tell a difference between sending a 0 and sending a 1. And then after sending, I sent my 1, I go back to sending a 0 by using the original pattern. And then the other modulation which we need to look at is amplitude modulation. This is more simplistic. So you just, in this case, I just send a sinus wave basically when I want to send some data, and otherwise I send nothing. But there are also different variations of this, so you can have different basically heights of your sinus wave to encode different states, or a 0 or a 1. So with this out of the way, let's look at a block diagram of how a chip usually looks like. Let's start from the very right. We have our antenna, and then it usually goes into like a radio part, which does the conversion from our analog signals to the digital domain. And then after this, we have a block which I call phi. This is then taking this digital data and doing the demodulation and getting actual frames out of the bits, basically. And after this is not always the case, but oftentimes you have something like a real-time core, or like some piece of hardware which does this, and you need something which handles the distributed coordination function, DCF. So, for example, sending acknowledgements in Wi-Fi. And then there is usually another, or the biggest core is for the MAC layer. I call it MAC core here, and you have some interconnect which is in between all of this. And then at the end you might have some interface to the host. In this case, it's PCIe. So let's zoom into this radio part a bit more. So now instead of going right to left, I go left to right. So I have the antenna on the left-hand side, and then I go to some amplification. And then the most interesting part is that we have basically two paths. So we have this upper and this lower path, and this is done by this mixer here. And what all this does is basically splitting up the signal into the part for the phase and the part for the amplitude. So the two modulation schemes we saw before, this is basically taken care of by these two paths. And then when we follow this path, we do some filtering, then we do some analog to digital conversion, and then out of this we get the actual bits which we can process further. And these are usually called I and Q. And this is what we will actually dump later on in our ICAP mode. And this is basically the most raw form we can get our hands on, which is the digital representation of our signal. So if we look at this IQ a bit more, we can draw a diagram like this. So we can have a Q on the x-axis or I on the y-axis. And unfortunately, we cannot say that like the amplitude is just one axis and the phase is the other one. But what we can do, we can just use our IQ data and draw a cross here. And then after we have this cross, we can have a vector starting from 0, 0 towards this cross. And then the length of this vector will be equal to the amplitude we received for this signal. And then the angle towards this vector starting from the x-axis, this will be our phase. So this way basically we can get towards modulating data. And in general, like complex numbers are often used to represent this. So if we take it a step further, we can say, okay, like a real simple scheme would be if I have like the amplitude and the phase for a signal, and I have maybe 4 different ways of changing this amplitude and phase, I can draw 4 different crosses. And then depending on in which quadrant I am, so upper left, for example, I encode the 0, 0, upper right is 0, 1, and so on. So basically this is already how modulation in Wi-Fi works. And this is what we want to get from the first mode, which we want to enable, which is ICAP mode. So how did we even get to this? And how did we find out about this? So there's this Windows tool called QA tool, and its purpose is for factory stuff. But we noticed that you can change some modes in here. You can change it to a test mode. And there is also a tool called ATED. If you use it in conjunction with a Wi-Fi router, it basically acts as a counterpart. And then you send commands from this UI towards this ATED. And then this ATED in return will call the kernel. And then it goes from there. And so the most interesting thing for us was here this FFT button, and we knew that this somehow needed to or will result in getting us the spectrum of the incoming signal, but we never got it to work with this actual tool, and we somehow wanted to make it work. And there was also like a CLI tool for Android, which was called a Wi-Fi test, which also provided similar FFT options, and the driver had lots of mentions of this ICAP mode. So what is this ICAP mode? It's called internal capture mode. And so these IQ data, which we had to look at before, this is basically used to receive this. So we were able to enable this for the MT6769. This chip uses the Gen 4M driver, and if you enable this, you actually don't need to have a connection to anything. You can just receive all the data coming into the chip. So the diagram looks a bit like this. So we have like a user space tool, which we call ICAP tool, and then we used an IOCTL interface to talk to the driver, which in return talks to the firmware. And the steps which we need to do are here on the bottom right side. So we first need to start the test mode. within test mode, we go into ICAP mode, then we set up the channel and bandwidth which we want to receive at, and then we can set up the ICAP mode itself. So first we need to set up a trigger. This trigger can be something similar, simple, which just says trigger right away, or it can even be based on MAC addresses. Then after this, there's this parameter called capture node. So this we believe, or we know what to set for to receive Wi-Fi IQ data, but we believe this whole mode can be used for different purposes within the chip, and you can set it to various things, but we know what value to use for Wi-Fi IQ data. Then after this, you just tell it how long it should capture, and then you basically just it will start capturing. Then you can just query it: Are you done? Are you done? Are you done? And if it's done, you can actually get the data. And then at the end, this is the IQ data you receive. So how this looks like in our implementation is we tested this on the Realme 6E. And the block diagram just has the ICAP tool within the Android phone, and then we have some Python script on a notebook which you can use to extract the IQ data. And for this we used the Android debug bridge, and we set up a TCP tunnel in order to send the data towards the notebook. And you can find this all of this in our GitHub repository here at the bottom. There will be a link also later on. And let's go for some demo. So what I do here, I have 3 windows. Let's look at the top left first. Here I'm setting up the TCP connection between the Android phone and the laptop basically. And then after this I'm running a makefile which sets all the right parameters in this tool we developed on Android side. And then after this, I can already start plotting the data. So this here is running on my local notebook. And then if we let this play out, so we see that this is starting to draw a real-time plot or waterfall plot of the IQ data which we receive. And then on the top, I have basically set up an HackRF, which is using a binary blob, just a single tone basically, and sending this on 2.412 gigahertz, which is Wi-Fi channel 1. And we should be able to see that the plot is basically changing based when we start sending this. So as you can see, the line is clearly changing, and therefore we are receiving this single tone which we were sending via the HackRF. Okay, that's for ICAP mode. Now to CSI. So what does CSI stand for? It stands for channel state information. It also consists of IQ data. Researchers often use this to implement fancy motion detection algorithms. Like you have seen at the very beginning, it was this picture where researchers were able to detect motion or people even behind walls just using Wi-Fi. So this is the stuff they use for this. CSI in general is captured for each subcarrier. So subcarrier in Wi-Fi means we don't only send on a single frequency, but we are actually sending on many frequency, 52 in this case for 802.11a. And this is done by using orthogonal frequency division multiplexing. And for each of these basically sub-frequencies, you get channel state information. And what this is actually used for is it's used basically as a known good value, which is sent by the sender, and then the receiver can take this value and compare it against what he knows should be the value. And then you basically have an estimation of how the channel does change the signal based on these differences. So let's see how this is actually working. So as I said, this is like the amplitude and phase offsets which are introduced by the channel. And so at the beginning we had this drawing which looked nice on the right hand side, but actually when you're receiving stuff, it might end up looking like on the left hand side. And if you look at this cross in particular, it's basically out of the region where it should be. So we said, okay, right, for every region we have a different bit pattern to encode, and this basically the phase and the amplitude variations were so big that it changed the quadrant, and we would decode it wrong. And you can use the CSI information to actually fix this and get it back to the right quadrant. So our CSI values, when we look at the Wi-Fi frame, they are stored in the preamble. The preamble consists of a short training field and a long training field, the symbol field and the actual data. And for our channel state information, we need to look at the long training field. So how did we come to explore this? There was a CSI patch which we found for MT76, which included hints to this mode, and we also had found a tool called MT76 Vendor, which provided options for CSI, but we never knew what exactly to set and how this will work. And then we found this repository by Lukas Weirek, who implemented a motion detection algorithm using Mediatek, and he basically had this implemented already, and using this we were able to know, okay, which parameters do we need to set, and how is the structure of the data which we receive once we enable this mode. So the block diagram for enabling this looks something like this. So we tested it on MT7981 using the MT76 driver. And in this case, we are not using IOCTL, but we are using the netlink interface. And the steps which we need to do are basically we set up the filter for the frames we want to receive, and in this case QoS data. Then we need to say, okay, once you receive these frames, how should they come to the kernel? In this case, we just say every time a CSI data is received, we send an event back to the driver, and then at the end we can enable the CSI mode and dump the data. So for this, we also have a quick demo. So this is a UI which we created, and just focus on the left-hand side. So the first row is for the first antenna, and the second row is for the second antenna. And the first step which I'm doing here is I'm setting a baseline for the amplitude. So basically, from this point on, I'm just interested into the differences which occur from a certain point in time. And then I will place my hand on the foreground here on this router, which is receiving this data. And we can see once I'm placing my hand there, the magnitude chart is clearly changing in a certain way. And same for the antenna 2 here on the bottom left. So this is a bit of a crude demo, but it shows that this really works. Okay, try to move on. So we tested this on MT7981, as I said, and we implemented it on 2 routers. So there's this Xiaomi AX3000T, which is a real cheap router, and it works there. And there's the OpenWRT1, and we also managed to make it work there. All you need is basically a patched MT76 driver and some additional OpenWRT packages, and you can find all of this in our repository at the bottom. Okay, back to Edoardo. Sorry.
Okay, so thank you, Daniel. And well, let's talk about the tools we are going to release, because during our adventure we have developed some tools for understanding better how it's possible to reverse engineer the Wi-Fi RAM firmware, essentially. And we are going to release some tools, for example, ROM dumper, which permits to read and create a ROM binary by reading the reg index and the regval file, because the ROM is always at a fixed address, so it's quite easy to implement. Then we made the MTK merge, which essentially is a tool which permits to merge the ROM patch and the Wi-Fi RAM firmware into a single L file, and well, this permits to have the complete view of the code which is running on the Wi-Fi firmware. And then we release also MTK Customizer. We haven't talked about it, but it's possible also to inject some NDS32 code at runtime while the chip is running. And this tool essentially is one of the possible way for accomplishing this task, because well, you can just manipulate the RAM firmware or the ROM patch firmware format and just add a new region, and well, this region is controlled by us, and well, this will run in the Wi-Fi firmware. And then we release the firmware log controller. Essentially, it permits to read the RAM debugging text, but from Android smartphone. And well, this can be useful if you want to take a look at the Android side. And well, then we are releasing RAM Reader, which essentially is still another way for interacting with the regindex and the regval trick. And with this tool, essentially, you can do a live disassembly of a specific memory regions inside the RAM firmware while the Wi-Fi hardware is running. And well, we also release a descrambler tool because we haven't talked about this, but some Mediatek Wi-Fi firmware are encrypted. And well, for example, the Mediatek 7961, which is a Wi-Fi 6 chipset, uses a simple XOR cipher, and we were able to reverse engineer it by exploring the boot ROM, because the decryption comes with the boot ROM. And also the Mediatek 7922, which is a Wi-Fi 6E chipset, make use of an AES-128 encryption. This was a little bit more complex to decrypt, but I was able to break the encryption, and well, as a result now we can also play with the decrypted firmware. And you can find everything at our GitHub repository. And well, let's talk about the lessons we have learned during our adventure, because we have dealt with their firmware. And well, when you are going to approach to the hardware reverse engineering, you always need to search if there are multiple drivers available online, because more data you have and better is to understand how the firmware works. And then GitHub search is your first ally for finding leaked health firmwares. This is valid also for Mediatek Wi-Fi firmware tool. And well, also always search for vendor tools under vendor/bin. This was quite useful for Android, because the Wi-Fi test tool Daniel talked before was found in this way. And also factory tools like the Q&A tools can be helpful to enable additional functionalities, which well is always cool. And well, we have still also some future research before finishing this talk, because for example, we want to enable the transmit of raw IQ data. We haven't tested this during our work. Then we want to do a further analysis of the Wi-Fi 7 hardware, which is going to be released by Mediatek, and we still need to test the Mediatek 7925 and 7927, which are RISC-V based Wi-Fi 7 firmware. And we want to test ICAP and CSI mode on different chipset. Of course, we want to try to unlock the CSI mode on a smartphone, because it seems that the latest smartphone have the CSI mode enabled in their firmware but not in their driver. So we want to play a little bit with it and see if it's possible to unlock it. And well, there is also a small problem with the NDS32 decompilation with some specific firmware. There are some opcodes which aren't still handled. We want to enhance the decompilation for the future, and we want to implement the firmware emulation too. And well, now is the Q&A time, so thank you for your attention. And well, here we have the links for our main repository. If you want to give a look, you are welcome. And if you have any question, we will be glad to answer them. Thank you very much.
We probably have time for one question. Yeah, go ahead.
Okay.
Fuck me, it's going to be a long question. Sorry about that. So how are you going about unlocking the CSI mode on smartphones because of this restriction, especially that Android now, or Google decided now to disengage in everything that has to do with sideloading because they're dicks. So.
Well, this is a really good question, because with at least the latest smartphone, I'm talking for Android 14 and 15, this is extremely complex to do. We should be able to, first we need to unlock the bootloader, of course, then we need to flash our custom kernel, and maybe we need to decide if we need to statically compile the Wi-Fi driver inside the kernel. And this is a way, of course, and then in this driver we need to enable a specific flag for enabling the CSI mode. We haven't found on the wild any smartphone which supports CSI, but it's possible to do, maybe. And well, then another way is to edit the file system, compile our own driver, and well, flash a new file system, but this is a quite complex procedure. So we don't know how to handle this, especially because the latest kernel make use of so-called GSI kernel, which is quite complex to modify. And well, we still need to think about this, but at least we are sure that also it's possible to put the support for CSI mode on MT76, so maybe some laptops will support it in the future. We don't know. We still need to work on this. Yeah.
Thank you.
But so you will always need to root your phone. I mean, the user space tool is using either IOCTL or NetLink, and both need root access to talk to the kernel.
Yeah.
Great questions. Thank you so much, gentlemen. That was absolutely fascinating. Thank you.